Hello and welcome to Calculus Tutorial. We are continuing our road through volume, and so we are now going to look at the washer method again, but this time we are doing rotations around the y-axis or any vertical axis. So a different direction for our rotation, but I'm hoping you can see that the overall method is basically the same as everything we've been doing so far. So when we rotate a region, and this is our region right here between these two functions, when we rotate that around the y-axis, I'm hoping you can see we have, again, a small circle cross-section and a larger circle cross-section. And those cross sections are going to be going up and down. So again, we're going to be taking the volume of the big and subtracting the volume of the small. That concept doesn't go away. And so for the big one, that will be equal to the integral of pi r squared. This time it will be dy. Because we are going vertically up and down with these cross sections, we are doing dy. And minus the integral, let me make that a big R, minus the integral of pi little r squared, again dy. So our question, as always, becomes, what is the radius? So your radius for your first circle goes from here to here. That is the x value. So this integral becomes the integral of pi x squared dy. And the other one is also going to be an x value. It goes from here all the way out to here. That is also an x value, but it's a different x value. Okay? And so the small x, the smaller radius, is going to be the x that comes from this function. And the other x will be the x that comes from, let me get a color that will actually contrast a little bit. The other x will come from this function. So we're again going to have to solve our equations, which yes, usually start out y equals something. We are going to have to do some algebra and turn those into x equals something. So we can substitute in the x here and substitute the x in there. But again, the idea of big minus small is still happening. So let's see how that works with some actual numbers in it now that we see the general concept. And to start us off, we're going to start with an easier one, and we're going to go around the y-axis before we try any vertical axis we want. So we're going to do that same problem we were just looking at. This time I'm giving you the actual functions though. So we have f of x is 1/4 x squared, so hopefully you can see the parabola here is f. And then the line y equals x is right here. And if we rotate that around the y-axis, we will get something that looks like this again. Now you don't necessarily need to visualize the three-dimensional object because your cross sections, the middle always starts at your axis of rotation. So our small cross section will go from there to there. And then your larger cross section will go out to the second function, there to there. And so our question is, what is the radius? So your radius goes from here to here. So that's your small one. Now that is an x value. So that is going to come from the line y equals x. So when we do our integral, which we saw was going to be pi big R squared dy, minus the integral of pi little r squared dy. The r's are, of course, the x values, not the y values for the function. So we put pi x squared dy minus the integral of pi r squared, x squared. Now this isn't completely mathematically correct, but I hope you're with me. These are not the same x's. As you can see, this x will be shorter than the big X that comes all the way out to here. So let's do the small one first. The small x comes from this equation. Well, this will be nice and easy because x is the same thing as y. So I can change that integral to be pi y squared dy. Just plug in y for x because they're equal. All right, now the other one has to use the x from the other equation. So this radius goes from here all the way out to there. That is again an x value, but it's the x value from this equation, not the linear one. And so we're going to take that equation, y equals 1/4 x squared, and solve for x on that equation. So we're going to multiply by 4 and then square root both sides. So x is going to equal 4y and then square root. And if you want to simplify that, that would be 2 square roots of y. Looks a little nicer, I suppose. Although actually we're going to square it, aren't we? So that square root is going to cancel out. So you might as well just use this one. So that will be the integral of pi times the value of x, which is the square root of 4y squared dy. Now, if you're going to do this by hand, you could continue taking those integrals, and we need some limits. So where are we going? Well, we're starting here at 0. But remember, we are going vertically, not horizontally. Actually, in this case, it wouldn't matter because it's the same, but we are going vertically, so we're going all the way up to the top. What is the y value where they cross? It looks like it's 4. Double check. If x is and y, where do these two equations cross? Do they actually cross at 4, 4? I think they do, because 4 squared is 16 divided by 4 is 4. And if you plug in 4, you obviously get 4. So they are, in fact, equal. So you have the top limit being 4. And so that is the equation that will give you the total volume. You can either evaluate it on your calculator, or actually that one you probably could do by hand. But the hard part is now over. All right, so that's around the y-axis. But what if we didn't rotate around the y-axis? How could we extend this idea to be around any vertical axis? So that's what we're going to do next. We got the y-axis down. Let's do a different vertical axis. Let's keep the same region, keep things easy for us. Only now we're going to do it around the line x equals 2. So around this axis. And so first your picture changes a little bit because you're going to go from here to there for your small circle. That's pretty bad, but it doesn't matter. And from here out to there for your big circle. Hopefully you can see your limits are still going to be from 0 to 4. We're going vertically, so this is going to be a dy. So we're still going to do the integral of pi big R squared dy minus the integral of pi little r squared dy. So we're still going to be going from 0 to 4 as well. That's not changing. But the radiuses are changing. The value for each radius is going to be bigger now. So your small one goes from here all the way to there. And so one way to think about this is big minus small. So your big value minus your little value. Numbers to the right are bigger than numbers to the left. So you're going to take this x value, so from here to here is still x, and subtract off this value. So for your small one, we'll call this little r. It is going to be the x value minus, and this value over here is -2. Hopefully you can just intuitively see that that's going to be a +2 to your x. So r is equal to x plus 2. And that is going to go in for little r. It is inside the square. So pi times x plus 2 squared dy. Because that was all the radius. This whole thing was the radius. You can see your parentheses there. All right, now the other one is still going to be the integral from 0 to 4 of pi times, now what is big R? Okay, so it is again, if I take this radius and I extend it out to here, that is still an x value, and we are still adding 2 to it. So this will again be x plus 2 squared dy. Again, that's kind of not the most amazing way to write it because those x's are not the same. So when we plug these in, this x over here comes from the smaller equation. And so the smaller equation is this one. Little r touches this equation. And so we are still here. Y equals x. So x equals y. So that is y plus 2. And over here we have to solve for y again. It will be the same as last time, but for the sake of it, here is our equation that touches the big R. So that will be y is equal to 1/4 x squared. We have to take our x's and turn them into y's. So multiply by 4, square root both sides, and x is equal to the square root of 4y. So we will have the square root of 4y, and then this plus 2 is outside that square root, so make sure that's clear. So the square root doesn't cancel quite as nicely this time. Okay, and that gives us our volume. So for the overall volume, we have big minus small, and then technically each radius is also big minus small. Remember, that's a double negative there. We are subtracting -2, which then becomes positive. Oftentimes on these, the integral is a little too complicated, so you'll either plug it into your calculator or just leave it that way and call it a day. All right, so we did one revolution around a vertical axis that wasn't the y-axis. That can sometimes look a little bit different if that rotation happens in a different direction, so we're going to do one more here. I think that's a picture of what it looks like there. Again, you don't really need the three-dimensional picture to do these. So let's just move that vertical axis and do the problem one more time. So this time we're going around the axis x equals 4. Oops, forgot to change this over here. That's also not a vertical line. My bad. X equals 4 is what we're doing. So we're doing the integral of big R minus the integral of little r in our volume formulas. So what is little r? And what is big R? All right. So again, they're both going to be x values. This is an x value. And so is this. Also an x value. One x value, the big x value comes from here, and the little x value comes from here. But that is not the actual radius. Oops, sorry. I kind of did those are going to come from x values, but those are not actually the x values. The x value of your function goes from here to here. But we want the distance from here to here. So how do we get this? That's going to be big R. How do we get that value? Well, we again do big minus small. So what is the big value? Well, the big value is the distance from here all the way to the end, which is 4. Minus, we want to get rid of all of this, and so that will just leave us with the radius we want, so it will be 4 minus x. And little r will be equal to the other 4 minus x. Maybe if I make that x small and this x big, you'll see the difference there between them. Alright, so 4 minus big X, 4 minus little x will give us both of those. Actually, that's probably not the best way, but we will solve those here in a second. So, the big radius will be the integral from 0 to 4 of pi times 4 minus x squared dy minus the integral from pi times 4 minus x squared dy. Again, these x's are different. So let's take a look at the big radius. Which x does the big radius use? So our big radius goes from here all the way to here. That is touching the linear function. So now this one is going to be our big, and this one is actually going to be our small. So because the big radius uses the linear, that is y equals x, they're the same thing, so I can just make a direct substitution. 4 minus y squared dy. And the small one, let me erase some of this, it's getting a little jumbled. So the small radius is now touching the quadratic. And so that will be 4 minus the x value of the quadratic. So you take your quadratic. You probably have this memorized already, but we'll multiply by 4 and square root both sides. X is equal to the square root of 4y. And so that will now be part of our small radius. Pi times 4 minus the square root of 4y squared dy. I think I forgot my limits here. 0 to 4. Everything looks complete. My variables match. So when you go around a vertical axis, you have to remember to change your x's into y's, so that way your variables match in your integrals. And make sure that you use the correct function when solving for y as well, or sorry, solving for x. That can sometimes get quite confusing. All right, that finishes up all of our rotational volumes. Hopefully that is making some sense.